All right, welcome everyone. Everyone who's at home. This is lessons 2 and 3 of the nuclear chemistry unit. We will be going over this worksheet, which is posted on Classroom. The goal for today is to be able to write nuclear equations for alpha decay, beta decay, and positron emission. The worksheet itself gives you some information and even goes through a sample problem, but we'll go through it together. So we'll do some of the questions together here so that you can follow along at home. In addition to being able to write nuclear equations for alpha, beta, and positron emission, the only other thing that you missed from this lesson was that each of the different types of decay have different penetrating powers. Alpha decay has low penetrating power, so even your skin can stop it. Beta plus, which is positron, and beta negative has medium penetrating power. While it would rip through skin, it would get stopped by a block of wood. And gamma rays, which are the highest energy rays and often accompany alpha, positron, and beta emissions, they will go through skin, they will go through wood, and only thick concrete can prevent them from going any further, which is why when you have nuclear reactors or nuclear bombs, when they're done, they have to be buried in thick cement blocks. Okay, so I'm going to hand the phone over and go over how to write equations for alpha, beta, and positron decay. You will need your reference table, in particular table N. If you see here, we have all the naturally occurring radioisotopes that you need to be concerned about, and the decay mode. B minus is beta, B plus is positron, and obviously the little a for alpha is alpha decay. Alpha decay tends to happen in really big nuclei that are trying to get smaller, whereas positron and beta emissions happen with the unfavorable ratio of protons to neutrons to try to balance it out to get to that 1-to-1 ratio for small nuclei and the 1.5-to-1 ratio for big fat nuclei. The other reason why you'll need your reference table to do this worksheet is for your periodic table of elements, because we're going to undergo transmutation during nuclear equations where one element becomes another, and you'll have to look up which element is formed. All right, so buckle up and let's learn how to write nuclear equations. Okay, so again, you can follow along on the worksheet. We're going to go through alpha decay first. So the example here is just like random isotope X. So alpha decay spits out, the nucleus spits out 2 protons and 2 neutrons. So the particle that gets spit out is really the nuclei of helium. Again, if you look at your periodic table, helium has 2 protons and 2 neutrons. So that's why we write the alpha particle just as helium. Obviously, the electrons wouldn't be coming with it at the time because there's so much energy, the ions would just be like flying off, but that's how we write it. Now, because this nucleus is spitting out 2 protons, it's not going to be the same element after that. It's going to be a different element, so here I'm just going to represent this as Y. And the atomic mass will have gone down by 4. Again, missing 2 protons and 2 neutrons. So the final atomic mass is going to be A minus 4, whatever we start with minus 4. We also spit out 2 protons, so the atomic number is going to go down by 2. So that is alpha decay. In beta decay, so again, on your reference table, this is indicated by beta minus, a neutron gets split into a proton and an electron. So that's the beta particle. We can represent the beta particle in 2 ways. One with a little e to indicate that it's an electron, or this notation and that little beta symbol. So let's do a real example for this one. Let's start with thorium 234, which again, if you look up on your reference table, undergoes beta decay. Thorium starts with 90 protons and 234 nucleons, which is the sum total of protons and neutrons. I look up on my reference table and I see that it undergoes beta decay, so I know that stays the same. If all I'm doing is transforming a neutron into a proton, the total number of neutrons and protons stays the same. So whatever I get, whatever new element I get, is going to have the same atomic mass. But what happens to the atomic number? Well, if a neutron becomes a proton, I'm going to have one more proton in that element. If I have an atom with 91 protons, it is no longer thorium, so I have to look at my reference table and look up which element has 91 protons. I look it up and I see that palladium has 91 protons. A good check when you're writing nuclear equations is to think about the atomic mass and the atomic number as almost two different equations. So I'm going to draw a line down the middle, right? My arrow is like an equal sign. Just like in algebra, I want to make sure that the top and the bottom balance out. I start with an atomic mass of 234, and here if I add up these two atomic masses, I end up with a total sum of 234. So it's a nice way to check to make sure you did your math correctly. I see like raised brows here. Is that any questions? Good?
Is that just because it's zero, or like is it always zero or no?
For beta, the change in mass, atomic mass will always be zero. I'll do the alpha one also. I'll do an example for alpha. Yeah.
What about minus -1?
Yeah, so for the atomic number, the same thing. I start with an atomic number of 90. If I write my beta particle like this, I see that on the bottom is -1 plus 91, so 91 minus 1 gives us 90. Let me do a real world example for alpha particles before going on to positron. So if I have, so again, I'll throw a little arrow to indicate this is alpha. If I have uranium 235, again, it starts with 92 protons and 235 nucleons. I spit out my alpha particle. I end up getting 231, 90. I end up with thorium, right? So again, the atomic number decreased by 2, the atomic mass decreased by 4. Again, if I look up the top and the bottom, the math works. So again, I draw my line, I have two different equations, 235 equals 4 plus 231, that math works. 92 equals 2 plus 90, yes?
There's no arrow.
That's supposed to be an arrow. Alright, so now I'm going to erase this and go over positron. And then we'll start to work on the worksheet. So in positron emission, again, this is beta plus. The two ways that you can write this are either like this, or you can put a little P for positron and write it like that. Now in positron emission, a proton ends up becoming a neutron. So again, the atomic mass does not change, and the atomic number goes down by 1. Because I'm losing a proton, it's becoming a neutron. So let's give an example. We have potassium 37. So we look on our reference table, we see, we could also write it like this with a little electron thing. So let's do it like that, because that's the way it is on your worksheet. So we see that potassium 37 undergoes positron emission. Okay. The atomic number goes down by 1. Somebody at an atomic number of 18. The atomic mass stays the same. The atomic mass will still be 37. And then I look on my reference table, which element has 18 protons? Argon. Check out my math, 37 equals 0 plus 37. Cool. 19 equals 1 plus 18, the bottom works out. Okay. So let's just do together the first question on the worksheet. Okay, so again, you're going to need your reference tables at home and in class. So we've got look up carbon 14 to figure out how many protons we're starting with. The question will always give you the atomic mass so that you can look it up on the reference table. And if I look up carbon, it has 6 protons. Now, for those of you at home, you're going to look up carbon 14 on table N. And if I look it up, I see that it undergoes B minus or beta decay. So I know that it's going to undergo beta decay. In beta decay, a neutron becomes a proton, so the atomic number increases by 1. The atomic mass stays the same. I look on my reference table to see which element has 7 protons, and that's nitrogen, and I'm done. Okay? For those of you at home, I will be posting an answer key to this probably later today. So please look over your answers after you're done. And I'll see you in January. For those of you here, please take about 15 minutes to work on this with the people around you, and then we'll go over it as a class.